All right, another example of the utility of this idea of Lorentz contraction. Let's consider the following example. Imagine that Gracie, she's just turned 18, very excited, and she decides that for her 19th birthday, she wants to celebrate it on the planet Zaxtar. And here's the issue. Zaxtar is pretty darn far away. It is, we are told, 1 billion light years away. So at first sight, the notion that Gracie could travel from Earth to the planet Zaxtar in 1 year, even though the distance between these guys is so incredibly far, that just seems kind of preposterous, right? So this distance over here is 1 billion light years. Is that what we were told? Yeah, goodness gracious. So this is 10 to the 9 light years. Can she travel from here to here in 1 year? Naively, no. But the answer actually is yes when we take into account all of the effects of relativity. Let's see how that goes. So from Gracie's view, if she is rushing along at a speed v, how long will she say? That is, what will she say is the distance from Earth to Zaxtar? Again, from her view, she's stationary. Zaxtar is rushing toward her. And because of that, the distance between Earth and Zaxtar will be length contracted. So she will say the distance is 10 to the 9 light years. But now she's going to multiply that by the contraction formula, 1 minus v over c squared. So that, from her view, is equal to the distance between Earth and Zaxtar that needs to be negotiated. And she wants to negotiate that in 1 year. So what does that mean? Well, if we look at velocity of Gracie times the time for Gracie, which I can just now hardwire in at 1 year, she wants velocity times time to cover that distance of 10 to the 9 times the square root of 1 minus v over c squared. So the question is there a v such that this equation will hold true, right? So that the distance that she covers, velocity times time in 1 year, will be equal to the Lorentz contracted distance from her view between the two objects. Well, this is just an equation now, right? We can just solve this equation, and it's straightforward to do that. And let's just work it all out for good measure. So let's square everybody up, because you have a square root over here that we want to solve for v within. So we have v squared times 1 year squared. This is equal to 10 to the 18 times 1 minus v over c squared. And the units, I'm just going to carry these over on this other side so that we have them. So it's light year squared. So this whole thing over here was in light years. So now we squared up, and the units are light years squared. Sometimes it's good to keep the units along for the ride just to ensure that at the end all the units work. That is a nice diagnostic to make sure that you haven't made any mistake. OK, so this is now a calculation that we can carry out. So let's bring all of the v squares together. And what do we have then? So we'll have v squared times, well, what do we get? So we have a v over c squared and a factor of 10 to the 18 over there. So let's now bring that over with a plus sign to the other side. So that's this guy over here. And the role of the c over here is just to change these units. So c, 1 light year per year. So when you take c squared, multiply by light years squared, the net result of that is to give us a year squared, which is exactly the right units that we have over here. I don't know if you need me to do that. OK, I'll quickly do it. So we have 1 light year per year. This quantity is squared. It's in the denominator over here, so it's 1 over that. And we're multiplying that by a factor of light years squared over here. And in my haste, I've actually left this out. So it's 1 light year per year, I should have said. So then when you put all these guys together, the years squared comes upstairs. and the units are exactly what you need them to be to combine them. Good. That was a little diversion. Now let's carry out the rest of the calculation. V squared times 1 plus 10 to the 18. What are we left with on the other side? Well, we're left with 10 to the 18. And then the fellow over there is just giving us a factor of 1 light year per year squared. So let's call that c squared. So that will get our result in the units of the speed of light. And now we can just solve for v squared. And it is equal to 10 to the 18 divided by 1 plus 10 to the 18 times c squared. And now if we just take the square root of that, the speed at which Gracie needs to travel is equal to the square root of 10 to the 18 over 10 to the 18 plus 1 times c. So that shows us that Gracie has her work cut out for her to achieve that high speed. But because of length contraction, she can actually travel all the way from here to here and only age 1 year. One way of thinking about that is time dilation. That's another way of solving the same problem. This time I'm wanting you to think about this in terms of length contraction for the other concept. From her view, from the view of a space traveler, she's not actually traveling that far. From our view, it's very far away, 1 billion light years away. From her view, it's not, because this factor over here, when v is very close to c, as this is very, very close to c, this factor here is very close to 0. So like the taxi cab, that distance is length contracted, Lorentz contracted, and she can, in fact, cover it in 1 year.